Welcome back, engineers. In my 20 years of teaching electromagnetic material properties, I see the exact same light bulb moment every single semester. It's that moment we finally bridge the gap between Ohm's macroscopic law, the one you've used in circuits a million times, and the actual chaotic atomic reality of electron mobility. Today, we're doing a deep dive into pages 8 and 9 of our text on metal conductivity to bridge that exact gap. So grab your notes and let's jump right in. Here's our roadmap for today. 1. An intro to electromagnetics conductivity. 2. The basic laws of electron movement. 3. Linking atomic properties to conductivity. 4. Practical problem solving, and 5. Advanced problems in copper. We'll move smoothly from the theoretical derivations on page 8 straight into the practical applications on page 9. Section 1. Let's kick things off by observing the drastic differences in material properties. It really all boils down to the presence or absence of free electrons. Just look at this staggering contrast. Silver's conductivity is sitting at an absolutely massive 6 times 10 to the 7th Siemens. Compare that to a good insulator at 10 to the negative 16th. That is a mind-blowing difference, right? And it sets the perfect stage for our core questions today. As outlined on page 8 of our text, we've got to ask ourselves two fundamental questions. First, how should Ohm's law be understood at this scale? And second, what is the actual mathematical link between the macroscopic conductivity we measure in the lab and these invisible atomic quantities? Section 2. To answer those big macroscopic questions, we need to shrink ourselves down to the atomic level and examine the fundamental forces acting on a single electron. Pay close attention to this derivation, folks. When there's no electric field, there's zero charge transfer. But the second we apply an electric field, E, the electron accelerates based on Newton's second law and the Lorentz force. Notice how the math brilliantly shows the applied electric field dictating the electron's resulting drift velocity step by step. It's classical mechanics at the subatomic scale. This brings us to a microscopic variable that is absolutely crucial: relaxation time, denoted by the Greek letter tau. Think of it like a timer. It dictates exactly how long an electron can freely accelerate before, bam, it inevitably collides with the lattice structure of the material. Section 3. Now for the fun part. Connecting the dots. We need to brilliantly link these microscopic electron movements back to the macroscopic material properties we can actually measure in the lab. By substituting our drift velocity, we mathematically prove that current density, J, is fundamentally tied to the number of electrons, their charge, and our new friend, relaxation time. What you are looking at right here is simply the microscopic formulation of Ohm's law. Isn't that elegant? And that leads us to electron mobility. This defining metric is the perfect mathematical bridge. It literally connects the measurable physical world to those invisible, chaotic atomic interactions we were just talking about. These handwritten derivations clearly illustrate the sheer elegance of defining mobility strictly in terms of fundamental constants, the electron's charge and mass, along with the relaxation time. This is the pure language of physics at work. Section 4. As I always tell my students, theory is completely useless without application. So let's skip ahead to page 9 and actually crunch some numbers together to prove what we've learned. We're going to use these 4 specific applied problems to mathematically prove exactly why silver is so vastly superior to an insulator or a semiconductor. Let's put our equations to the test. Check out this absolutely massive number, 5.8 times 10 to the 28th. That represents the conduction electrons per cubic meter in silver. This colossal density is the real secret behind silver's immense ability to conduct electricity. It's like having an impossibly wide highway for traffic. When we compare silver, an insulator, and a semiconductor side by side, using the data from our first problem, the picture becomes crystal clear. The raw electron density, N, completely dictates the overall conductivity. The insulator only has 10 to the 6 electrons, which perfectly explains why its conductivity is practically 0. Moving on to problem 2, with germanium, a classic semiconductor. When we calculate its specific relaxation time, we can clearly see how its drift velocity scales directly as we crank up the applied electric field from 2 to 4 to 8 volts per centimeter. Section 5. Let's bring it all home with copper. This is a highly relevant conductive material you will encounter constantly in your real-world engineering careers, and it's exactly what problems 3 and 4 cover. This incredibly tiny fraction of a second, 2.5 times 10 to the negative 14th, is the calculated relaxation time for a single electron in copper. This number really highlights the extreme, almost incomprehensible scales of quantum physics happening inside the wiring of your house right this very second. Now, I want you to think about this critically. If an electron's random mean speed is a blistering 1 million meters per second, what happens if we impose a seemingly tiny ordered drift velocity of just 0.1% of that speed? How does that translate into real-world current? The math here is genuinely shocking. It reveals that even a microscopic fraction of ordered movement creates a truly massive, frankly catastrophic amount of current. We're talking 11 million amps trying to force their way through a 1 millimeter wire. Obviously, in reality, that wire would vaporize in a fraction of a millisecond. And that perfectly encapsulates our core lesson today. As you leave this explainer, I want you to ask yourselves, what other simple macroscopic engineering laws are hiding a chaotic, incredibly powerful atomic reality just waiting to be uncovered? Keep questioning things, keep crunching the numbers, and I'll see you next time.